This talk introduces a fast, low-cost magnesiothermic route to synthesize the max phase Ti3SiC2 and explains the structure processing microstructure links we validated. Max phases combine metallic conductivity and machinability with ceramic-level thermal stability and oxidation resistance, which is why they keep showing up in high-temperature structural concepts. Our focus is to demonstrate that a compact, wafer-assisted magnesiothermic setup can produce Ti3SiC2 nanocrystallites without resorting to high-pressure or tightly controlled atmospheres. The synthesis concept is intentionally simple to lower the barrier to adoption. We mixed titanium, silicon, and carbon nanotubes in a 3:1:2 molar ratio, compacted the blend into pellets, and sandwiched each pellet between two magnesium wafers that act as an in-situ reductant and heat source. The assembly was placed in a reactor with CO2 flow to moderate ignition and gas evolution. The processing sequence emphasizes controllable ignition, rapid reaction, and straightforward post-treatment. Ignition was done with a graphite electrode using an AC arc welder. The reaction ran for about 5 minutes until Mg was consumed, and the pellet was then recovered and leached in 20% HCl to remove MgO and other soluble byproducts. This sequence was chosen to privilege speed, reproducibility, and compatibility with readily available hardware. The phase analysis confirms the formation of Ti3SC2 together with a residual TIC fraction. XRD indexed with standard databases shows hexagonal Ti3SC2, space group P63mm, coexisting with cubic 3IM. The quantitative assessment indicates approximately 56.4% Ti3SiC2 and 43.6% TIC, which gives us a clear purity target for the next optimization loop. The microstructural evidence supports nanocrystalline max formation with characteristic lattice signatures. Scherer analysis yields an average crystallite size near 48.4 nanometers after instrumental correction. TM shows polygonal agglomerates typical of brittle ceramic fractures. EDS maps confirm a homogeneous TIC distribution, and HRTEM resolves planes consistent with TIC 200 and 111, while SACE patterns are fully indexable to the observed phases. The interpretation points to magnesium-driven reduction and localized thermal spikes as the drivers of phase selection. The wafer geometry supplies intimate contact, high local activity, and brief high-temperature excursions that can favor both max formation and competing TIC nucleation. The CO2 sweep appears to help with gas management rather than acting as an oxidant under these conditions. The advantages over conventional routes are cost, speed, and minimal infrastructure. Unlike hot pressing or inert gas furnace schedules, this route avoids high pressure and tightly controlled atmospheres, cuts reaction times to minutes, and uses commodity inputs. Those attributes matter if the community wants scalable screening of max chemistries beyond TIC. The limitations are clear, and they define the optimization plan. To suppress TIC and raise Ti3SiC2 purity, we will tune magnesium wafer thickness, pellet density, and ignition energy while adding hold time control and thermal buffering. We will also explore pre-alloying of TISI and adjust carbon activity to steer the reaction path. The broader impact is a compact protocol that could be generalized to other max systems and integrated with downstream property testing. With phase purity improved, we will move to oxidation kinetics, mechanical probing, and device-relevant evaluations under thermal cycling to benchmark this route against conventional syntheses. In closing, this work shows that a 5-minute magnesiothermic process can deliver nanocrystalline Ti3SiC2 with a defined optimization path to higher purity. We see this as a pragmatic bridge between exploratory max research and scalable processing that is compatible with real-world constraints in aerospace and energy applications. Thank you.